So, first of all, thanks to organizers for organizing this wonderful meeting. I'm really learning a lot and seeing a lot from different fields, so that's enjoyable. And thank Gerhard for inviting me. When he invited me, I said, "Are you sure you want me here? I see ontology and different interpretation of quantum mechanics, and I have nothing there." But it was also the Bohm centennial, and since I had some new experiments on Aharonov-Bohm effect, that might then be appropriate. Okay, so I will say the word ontology once, and that was it. Okay, so let's oh yeah, maybe twice. So here we go. So this is the topic. First, before I forget, here are the acknowledgements. So the experiments have been done in Jo Verbeek's group with 2 of his people. And Professor Uiterwaal made some of the laser stuff available, who is in Nebraska. And then some of my graduate students did different parts of experiments or the theory belonging to the experiment. And of course, funding by the National Science Foundation. All right, so probably, maybe for this group not necessary, but let's just first define what the Aharonov-Bohm effect is. What we have is some magnetic flux. The blue are the field lines, the green are the vector potential lines, and we have 2 paths of an electron diffraction that pass by this. And then what you get is you get a phase shift that can be expressed this particular way, which was, of course, talked about in detail in the 1959 famous paper by Aharonov-Bohm. And that is all wonderful. And then, of course, experimentally, a year later, Chambers already did the first experiment. He had a magnetic whisker, so this needle was magnetized. And you see at different heights on your screen, you see a phase shift that depends on how much magnetic flux you enclose. So you get tilted field line, because as you go down, you enclose more and more magnetic flux. And of course, there have been beautiful experiments done by Tonemora later on, where there is a toroid which was magnetized. Some electrons pass through the center, some on the outside, and you can see that there's a phase shift. And the phase shift also indicates there's flux quantization in small structures. And that's, of course, lovely and beautiful stuff. Right? So this is all confirmed. Now, what is the significance of that effect? Well, there we can have very long discussions, but I'll just keep it fairly short. If you look, for instance, at what Tonemora, who did one of the experiments, and Franco Nori have to say about this, they say it's controversial in part of the modern physical aversion expressed by Einstein and others to the concept of action of a distance. Something like that was mentioned here before, but in the context of 2 particles. Here the context is 1 particle, where sometimes people talk about that the magnetic flux, the B field, has a non-local action on the electrons outside, or you could say that you have a local action here by the vector potential, the green lines, right? And some people say, no, I want to have a theory described purely in local, measurable quantities, and since the vector potential, of course, at one location is not measurable because it's a gauge invariant property, then some people try to construct a theory that is only in terms of fields, right? In the end, fields, you might also say forces, through Lorentz forces. So the question is, what is then special about it? Well, this might summarize it. There is no force, that's the claim in the literature, in the books, but there's still an effect, right? That's what you find in many quantum mechanics textbooks. And that is, of course, something that is pertinent to, can you find local descriptions or not? So we'll focus on the question, is there a force present for the Aharonov-Bohm effect? Okay? Okay, so what is the way that this came to me? I was working on Zeilinger's group, and Zeilinger has Zeilinger's dispersivity theorem that is pertinent to AB effect, and he explained it to me in this way. So I wrote at some point some code to visualize this. So imagine you have a magnetic flux, and your electron diffraction, where 2 paths surround this, fly by that solenoid. Then let's actually first, hang on, where's my marker here? Let's turn on the solenoid, if we can. And then let's run that wave packet by. So you would get something like this. Now you may not notice anything happening that is different left and right, but if I stop it and would have done this experiment at different strength of the solenoid, you would see that the top picture, the phase shifts forward, and the bottom, it shifts backwards. So you get a phase shift for the relative waves that move on the left or the right, right? That would be the standard interpretation of what the Aharonov-Bohm fringes tell you. So there's a phase shift due to the enclosed magnetic flux.
Does the picture show the real part of the wave function?
Yeah, in this case, it's just the real part. And of course, you could do the imaginary part and add them up and do the probability, and you get the same type of picture, but of course, above zero. Yes? Yeah. So you can state that how do you do this? How do you make such a picture? Well, you just take a plane wave, you stick in a phase, and if this phase is k independent, then this is the result you get. So this is done with something like 21 wave components to make the wave packet, and you can make a nice little picture of this. The other thing, there's another possibility, which is this one. So here I put dispersion in. So I made this phase dependent on k. And so what you then get is, if we start this thing, the experiment would look like this. One wave gets accelerated, the other one delayed, and one is ahead, one is behind. And if you change the strength of the solenoid and do this again and again, then you see that the wave packet shifts. And so now you would also get a phase shift. Now that would be if there is dispersion. So you imagine, your two wave packets, and either, this is the wave packet and it slides like this, or it's just a multiplicity phase. So how can you distinguish between the two? Now that's what Zeilinger explained to me. He said, this is the crucial part, the defining part of the Aharonov-Bohm effect. He said, look, if it's just a multiplicative phase, then if you change the magnetization of the solenoid, your fringes just keep on going and going. But if it's a dispersion effect with dispersion, you get a bump. And of course, so we should measure experimentally the dispersionless nature of the Aharonov-Bohm effect as its defining property. Okay? Now that has never been done yet. Now, interestingly, I just read a paper 3 days ago that Carl Berggren at MIT made a monolithic electron interferometer that's, I think, big enough to contain fluxes that are large enough, so people, I think, will at some point be capable of doing things like this. But it hadn't been done yet. So, well, I knew that. I was working on electron interferometry, so I never forgot about this stuff. And at some point I had this idea, why not do something simpler? Why not just measure the delay of the wave packet? If you want to rule out that there are forces, right, or that you want to show it's dispersionless, then why not just do a timing experiment? You have a wave packet that flies by a solenoid and see what happens. Now, so at some point Mark Kasevich at Stanford and Peter Hommelhoff developed, about 2006, tungsten nanotips that you hit with a femtosecond laser, electrons comes out. We did an experiment with pump probe and showed those pulses are faster than 100 femtosecond. That nowadays they proved even that you have attosecond responses. They're really beautiful experiments, beautiful area. But you can do this to do some physics. So you fly by an activated solenoid and you see when you arrive. Now, how big of a force should we look for? Well, you just equate the phase shift in this picture to be the same as this. And then you should have a force that gives this type of displacement, depending on the enclosed magnetic flux, etc. Yes? You might say, well, isn't that how big of a force should you look for? Well, you get this number. And then you might say maybe that's very unlikely to have such a coincidence. Well, there was another paper by Tim Boyer who most people kind of disregard because he comes up with fully classical explanations for this, but it's nice that he gives a prediction, and the prediction is based on this idea that the electron, as it passes a solenoid, sets up Lorentz forces in the solenoid, and if you just calculate that, you get this expression. Now, if there's and that's a big if there's a back action of the solenoid on the electron, then you would expect there be a delay. You calculate that, and it turns out that that delay is exactly of the right magnitude. Okay? That is interesting, that maybe it wasn't so crazy to look for this. So when I did this experiment in my group, then I thought, oh wow, this is something that maybe it goes out against what the books are saying. I mean, that would be a shock, right? So it's not so unlikely. Then you do the experiment. Here's the little heart of it. It's a tiny little vacuum chamber. In there's a metal tip. You put some flux in, you do actually two, you close it with ferromagnets to close the magnetic flux so nothing leaks out. You do a timing, there's a channeltron on one side. Here's the tip in the center that's illuminated with a femtosecond laser. You close it up and you time. What you get is this. So in other words, this is what everybody says in the books, where the data is, and this is what Boyer said. And then you say, okay, that is, you confirm what's in the book. And it was nicely received, it was a PRL. We measured, by the way, the flux also in situ, but with induction. So that's maybe not, you have to do that. Because, of course, you have here a bunch of zeros. So they say, gee, did you actually do an experiment or did you just put zeros there? So, right? But the deal is we did another one just to make sure that we could do something. There was another experiment which is another AB effect, or claimed to be an AB effect. So the first version is actually an AB effect that was in the original paper. If you enclose a magnetic flux, you get a phase shift. But if you enclose an electric flux, you also get a phase shift. It's also in the 1959 paper. Now, that was translated at some point into this thing. There was a PRL in 1985 where the plates were replaced by wires that were charged. And then Matthieu Symposium did a beautiful experiment, by the way, but it was interpreted as saying that it's a type 2 non-local phenomenon predicted by Aharonov, etc. The deal is, in this case, if you do the experiment, which we did, so we made 2 wires, here are the 2 wires, we fly by, you activate them, you do the timing, then what you get is this. So in other words, here is the wire voltage, there is delay of the pulse, here the pulses do shift. This is Boyer's theory that predicted delays. The data around 0 voltage matches nicely. And of course, if you do a simulation, which we did to take into account some fringing fields, then actually you see the agreement is quite good. And this is absolutely not an Aharonov-Bohm effect. So you have to be careful. That was claimed in PRL to be a non-local effect, but it's not. So some are not, and it also demonstrates that we can hunt for these things. So in this stuff, one of the original magnetic AB effects, all seems to be well. And it is, actually. So then, of course, there was at that time some media, blah, blah, blah. But the point is, then I wrote to Akira Tonomura, had done that beautiful flux quantization experiment. And I say, oh, let's do physics today. Because we have the phase shift. Now we have shown that there is no force, which everybody was assuming. So we could put it together, have a little overview, and then say, what else could you do, right? And, well, okay, so we did one paper. I visited Tonomura in Japan. And then soon after, he actually died. And there was a memorial book where they asked collaborators to put papers in. So I wrote a paper on there. And that was picked up. That was one of these widely ignored papers, right, that I sometimes write. But there was one person who picked up on it, which is this one. So Michael Berry picked up on that. I was very pleased with that. He's the only one who ever commented on that paper, so it's good. So I just received my copy of the Tonomura memorial book. And I was interested in your article, blah, blah. This is a matter, I've been interested with the conclusion that there is an AB force. And I said, oh, yeah, okay. And then I said, okay, hang on. You know, I've published this and people commented in multiple places and it's all fine. So what's going on here? And it is a quantum force. I said, okay, what is that? I didn't know at the time. And it is in agreement with your correspondence principle argument indicating there's no classical force. So apparently I said something that was not wrong, which is not too likely, but every once in a while it happens. So one in agreement with the suggestion in your paper, it is to investigate whether a beam is deflected. So now you have that solenoid, right? Electrons fly by, there's no delay, but you can still look if there's a deflection. Because that would also indicate, of course, operationally in experimental sense, if there was a force present, right? And thus if there's a local interpretation, perhaps or not, or maybe not. Maybe the quantum force doesn't allow that. So this was, I was delighted at that. Then I read the paper, which Shelenkov started in 1999, and Bear had an elucidation of that in a year later. Both very nice papers. And yes, and so then at that time I said, oh gee, maybe we can experiment. The experiment is hard because it's even harder than the other ones. But then, let's see. Yeah, so going back to what was one of the things I said in the paper. This is something I still don't understand, so I'll expose my ignorance. So I said something like this. If this is a density matrix of a wave packet, and here is the probability online, so this is a position basis, and here are the coherence terms. If there's something that decoheres, then the coherence elements go away, right? And you could say that in decoherence theory, there's one visualization how you can approach the classical limit, perhaps. But as soon as you do that, if you think of that wave packet as described as a superposition of coherent wave packs, then if there is a dispersionless interaction, each of those wave packets doesn't shift. So if there's a dispersionless force, nothing shifts. So the sum of this also doesn't shift. But in the classical limit, that force can give rise to a shift. And we wrote then a series of papers, hang on. Oh yeah, we wrote a series of papers here where we talked about dispersionless forces. We gave examples of this theory. We followed experiment. Actually, we ruled out the existence of those approximate dispersionless forces. And so even that could not explain what was going on, but it is still, since those things in principle apparently can exist, the classical limit is completely unclear to me. You have a wave packet, none of the parts, even if you cut it up in different parts, nothing shifts, but in the limit of a classical particle, the force will shift. I don't know how to approach the classical limit in that case, which really bugs me. And apparently Barry thought that was a reasonable, I think what he's saying, that's a reasonable argumentation. It's interesting. Okay, so I gave a talk last year, and so fast forward in Europe, and there was a speaker, Jo Verbeek, who I hadn't met at the time yet, who works in the University of Antwerp, and he had done experiments where he took a magnetized nano rod, and he put that in a machine, something like this, where you have a little aperture, and in there, I put actually a solenoid in there, but it's really a nano rod, and you put an electron beam through it, and you look at the picture there. He didn't do it for the purpose to figure out that there is a Cherenkov-Barry force or something like that. He did it for the purpose of studying that nanorod, right? Because you maybe can get an image and you can look at this. And I looked at that, and he had an image that looked where one side is brighter than the other. But since Barry had told me his paper and I read it, he had calculated, Barry, things like this. So this is the beam, the symmetric blob in the center is the beam if the magnetization is off. Then you turn on the magnetization, and you get a small blob and a big blob. Then you go to a pi phase shift, and it is again symmetric, and a 2 pi phase shift gives you back the original peak again. So you note that for the little blob and the big blob, the expectation value is actually not centered, right? And it's actually shifted to the right. Hence, there is a Cherenkov-Barry force operationally, because the expectation value shifts. Yes? And so that was interesting. Then I started talking to Jo and say, gee, you're maybe sitting on something that's really, really cool. So why don't we do this? We write a quick path integral code. We first confirm that we understand this, and the vague, let's say the shadow on it is actually the result of our path integral stuff. And if you have that for what Barry did here, Cherenkov did, they consider Gaussian wave packets. But if you have here truncated wave packets in 2 dimension with part blocked, you've got to take those things into account. So if you path integral, you can put all the little deleterious stuff in there and see what happens, right? And so then we said, gee, is that what you got? And here is the outcome of that experiment. So we have, it's really a fancy electron microscope. And we're talking to a $5 to $10 million device, which is really for general purpose. It's an electron microscope institute what they have there. And this object is then made out of a membrane of silicon nitride. You cut in there the 5 micron hole. This is an electron microscope image that on it is then put a 30 micron, so let's say about from here to here, nickel material with a 1 nanometer gold coating. It's about 600 nanometers wide. That thing automatically magnetized because there's flux quantization. They can see that because what you can do, instead of illuminating this with a plane wave, you can focus on this area and then take an image of it. So either you're in focus or out of focus, and you can switch back and forth to see what is going on, right? And then you can even see the little leakage fields here. I don't have those pictures here, but that's what you can do. So they determined the magnetization of this in that technique, off-axis holography, and said, here's the value for your magnetic flux. So there we go. We go on the path integral calculation and say you stick it in and see if you get the right answer. And then the path integral calculation lies on top of it rather spectacularly well. And thus, and the adjusting, there was an adjustment of 4% in the value of the magnetization we had to make to get this good of an agreement. So we say, okay, so Barry predicts that it shifts, which we cannot actually see because that you cannot calibrate. But the other prediction he makes is that the pattern is asymmetric, and that we observe. And that's nice. And then you demagnetize this bar by bombarding it with electrons. At some point, there's a phase transition, bloop, the magnetization is gone, and then you measure the non-magnetized spectrum, and so no adjustable parameters, there it is. So that is the thing that we just submitted to PRL, and it's now under review, and we hope that the referees are gentle and nice. All right, so here we go. Now, at this point, though, there's two questions. First is maybe, what is quantum about it? So we also did a de Boyer-Bohm calculation where we, a little bit behind this thing, we calculate the wave function with Pythagorean. We then figure out what the potential is, and you notice that the left and the right are not the same, and it's asymmetric. And if you integrate over this thing, it's non-zero. That's where the non-zero force comes from, and it comes from Q. So indeed, it is the quantum potential that gives rise to a quantum force, while the regular potential, that would depend on A and phi, is still completely zero there. There's no gradients of those that are relevant, right? That's why it's a quantum force. And you could also follow a paper from Keating and Robbins, which I have difficulty following, but nevertheless, Barry tells me this is rather theoretically difficult to do, but they show there with a quantum force operator also that it is a quantum force, yes? Next thing is, but wait, the AB effect was supposed to occur without forces, right? Because of this dispersivity. What is that really? Well, Zeilinger told me that, right? That was that picture of wave packets that go back by that magnetized thing. So what is going on there? Take a wave packet, and this is, by the way, an argument that Murray Pashkane published to explain Zeilinger's dispersivity theorem. And he said, okay, let's take a wave packet with plane waves, and let's say that the interaction is due to a phase shift here that depends on the k vector of each of the plane waves. Now, if you do that, then you can just do some algebra and figure out that your expectation value of position is, well, this term where you start, plus the average velocity times time, plus an additional term. Now, if you compare it to Ehrenfest's theorem, without real potentials there, you would expect to get this, and you can thus immediately conclude that if you are force-free, that there is no dispersion, right? Because the phase shift is independent of velocity. So that is the dispersionless, that's Zeilinger's dispersivity theorem. And hence, that is underlying some things you see on the books, that this effect is force-free. But wait, Barry now says that there is a quantum force. How do you marry the two? What is going on? Is our understanding wrong? Well, there's a simple argument. So I looked at this, I was worried about this for quite a long time, but then came up with this argument. It's very simple, actually. If you look here, and you consider what this interaction does, it writes a phase shift as a function of position. So it's not delta k, it's delta y. Now, you might say, gee, you just Fourier transform to k-space and you're happy. But keep in mind, this original wave function is already here, gives the Fourier transform this one. An interaction then, if you Fourier transform this, you pick up in here an amplitude that's k-dependent. So you cannot just write any interaction in this particular way. So the assumption that Zeilinger had that this describes the interaction does not hold generally for the Aharonov-Bohm physical scenario. And hence, you can have quantum forces. So conclusion, the Aharonov-Bohm effect is accompanied by a quantum force, and in that sense, my opinion is, perfect, that the books should be very careful to say there's no force accompanying what is it, the Aharonov-Bohm effect. It needs to be rewritten in that sense. And what does it mean for locality and non-locality? That would be another talk. So maybe next time. All right, that's it.